So, for today's test, we're doing chapters 1 through 4 calculator, and on the board we have questions 1 and 2 because I was able to fit them. So for our first question, we have to find the limit as x approaches infinity. So here's our graph f, and immediately what sticks out is that we have a dotted line going across at 55. So this doesn't automatically mean that the limit of f of x equals 55. So the way to calculate the limit as x approaches infinity of this graph is essentially what a limit is where, or is like the y value of the function at a certain point. So in this case, we're trying to figure out what the y value of the graph at infinity looks like. So since infinity isn't an actual number, we're just trying to approximate as the line continues to go further across the x-axis, where will it float around? So again, with the whole limit thing, if your line was y equals x and you were trying to find the limit as x approaches 0, the limit is 0 because when x is 0, y is 0. So we're doing the same exact thing here. We're saying, okay, when x is infinity in this case, or some extremely large number, what is it going to be closest to? So we can see that f starts to plateau at 55. So this is an indicator that as time goes on, 55 is somewhat of an asymptote in this equation. And so f will start to level out more and more and more the further we go down the x-axis at 55, indicating that 55 is the limit of f of x as x approaches infinity. So for question 2, we had to find the closest point to negative 5, 1 on the graph f of x equals x plus 1 squared. So one thing that you can do really quickly is put negative 5, 1 on a graph and then graph all the other points. I didn't include the points because I didn't think there would be enough space to put them. And then you can just see which one is closest by eyeballing it. You can also do something with triangles. So for example, if I want to evaluate the distance between negative 5, 1 and c, we can make a triangle where this is the hypotenuse and then we have our two legs. So we can square the legs, add them together, and then take the square root of that to find the distance here. And whichever point has the smallest distance in terms of the hypotenuse length is the closest point. As for how to do this with calculus, one way you can do it is you can take an arbitrary point from the graph, you can label it as x, comma, and then since this will produce your y value of all these points, you can plug in this function for your y value. Then you take negative 5, 1, and your arbitrary point, which would be x, comma, x plus 1 squared. Plug them into the distance formula so that you get one nice equation. Then you take the derivative of that equation, find where the derivative is equal to 0, and then evaluate those x values in your original distance formula to find out which one is the closest to negative 5, 1. Alright, so for question 3, we have to find the integral, or the indefinite integral of 3 secant y in parentheses tangent y minus secant y dy. So this one's really simple. All we have to do is distribute 3 secant y into the parentheses, which is our first step right here. We know that secant y tangent y is just the derivative of secant y, so we get 3 secant y from here. The derivative of tangent y is secant squared y, so we can just substitute tangent y in for secant squared y since we have the integral, and then we have our constant of integration. Alright, so in question 4, we have seedlings and we're trying to find an equation that will tell us at whatever time how tall they are. So what we know is that the difference in height over difference in time is 2.5t plus 6, and we know that when time equals 0, or when we're starting to measure the amount of time, the seedlings are 11 inches tall. So the first thing that we want to do to find this equation is to integrate this equation right here. So this is effectively in a derivative that tells us the rate at which the plants are growing, not how tall the plants are. So we can utilize this to be part of the equation that we use to find out how tall the plants actually are. So when we integrate this, we get the integral of 2.5t plus 6 in parentheses because we have an addition sign, dt. This becomes 2.5t squared over 2 because we have to add the power on the bottom, so we divide by the power on the bottom, plus the 6t, t is to the 1 power, so we don't have to divide by 1, and then we have our constant of integration. 2.5 divided by 2 is 1.25, and then we have the t squared still, plus the 6t, and then our constant of integration. So at t equals 0, the seedlings are 11 inches tall. So what we can do is we can set this equation equal to 11. We plug in 0 for t. I forgot a t squared here, but still 0 squared is 0, times 1.25 is 0. So we get 0 plus 6 times 0 is 0, so another 0 plus c equals 11, so we get 0 plus c equals 11, which means c is equal to 11, which means that in this equation our constant is equal to 11, so our equation becomes 1.25t squared plus 6t plus 11. On question 5, we have to find the integral of f of x from 0 to 6. So the original f of x equation is just a bunch of different line segments. So the actual f of x equation is just this part right here. That's kind of a trapezoidal shape. So to find the integral from 0 to 6, the most efficient method, since we don't have an actual equation, is just to use geometric formulas. So we're going to start with this rectangle that I drew in. So this has a base of 1, since this point right here is 4 on the graph. So that's 1, and then we go up to 2 as indicated over here. 1 times 2 is 2, so the area of this is 2. This triangle has a height of 2 and a base of 2, and then 2 times 2 is 4. Then in the triangle formula we have to multiply by a 1/2 as well, so that also gives us 2. This is the exact same shape, just flipped over to the other side of the rectangle, so we get another area of 2. But then right here, since we're starting underneath the x-axis, this will actually be a negative in our total area. So this has a height of 1 and a base of 1. So we get 1 because this is positive, times negative 1 because this is negative, times 1/2. And then we get negative 1 times 1/2, which equals negative 1/2, as indicated over here. So then we can just add all of these up together, starting with negative 1/2, since we're going from 0 to 6, so we just add this way. Then we have a 2, a 2, and a 2. We can simplify this into 1/2, or 1 and 1/2, plus 2 plus 2, 1 and a half plus 4, and then we get 5 and a half. Questions 6 and 7 are 2 problems you can solve really quick using your calculator, and they're very compact problems. So for 6, we're just trying to find the integral from 2 to 8 of 9, absolute value t squared minus 9 dt. You can simply just factor out the 9, do the integral from 2 to 8 of t squared minus 9 dt, and then plug that into your calculator, and it comes out to 1074. Again, if you handwritten it, it would take longer, plus you would have to account for positives and negatives, since this is an absolute value equation, whereas just by simply plugging it into your calculator is quicker to solve. For 7, we're trying to figure out the average volume of air pumped into the lungs on a 5-second respiratory cycle. So you're given this volume equation. We were also told that since it's a 5-second respiratory cycle, we're solving from 0 to 5, and because it's the average volume, integrals are involved as well as a fraction on the outside of the integral. So what this means is, since we're looking for an average value of something, we have 1 over b minus a, which would be 5 minus 0. Then the integral from a to b, which is the integral from 0 to 5 of our volume equation. Again, something you can plug into your calculator really quick and get 0.5325 liters for. On question 8, we have to solve the integral of 7 minus z in parentheses times the square root of z dz. To start, you can distribute the square root of z into the parentheses, so you get 7 square root of z minus z square root of z dz. Then what happens is we have to find the integral of this, of course, so we have exponent rules becoming involved. So when you do the integral, you have to add 1 to the exponent. So in the case of the square root of z, that's z to the 1/2 power. You add 1 to the exponent, that's z to the 3/2. And when you divide by the 3/2, it's the same as multiplying by the reciprocal. So what you end up getting is 2 times z to the 3/2 over 3. And then the same thing happens with your second term. It's like multiplying by the reciprocal of your exponent. So for the second term, we have a z times the square root of z. So in this case, what we can do is we can declare that z to the 3/2 already. So when we add 1 to the 3/2, we get 5 over 2. So that's why we have a 5 here and a 3 here, is because this combined is already to the 3/2. So adding 1 just makes it to the 5/2. We again multiply this top part by 2, and then we have a plus c because it's our constant of integration. So when we come down here, 2 times 7 is 14. We keep the z to the 3/2, put it over 3. Then we subtract this part right here. 2 times c to the 5/2 is 2c to the 5/2 over 5 plus c. So for question 9, we're asked to use the trapezoid rule to solve the integral from 0 to 2 of 3x squared dx, and n equals 4. So n equals 4 means that we're going to have 4 different trapezoids that have an equal height. Since we're solving from 0 to 2, we have 2, and then since we have to split it into 4 equal trapezoids, we have to divide by 4. This solves to 1/2. Since 1/2 is a height and it's being multiplied by this ratio right here, we can just factor it out and then put this in parentheses. So we can just add up all of the a plus b over 2's in parentheses and multiply by 1/2. So when x equals 0, y equals 0, and when x equals 1/2, y equals 3/4. So when you add those two together, you get 3 over 4 divided by 2, which is 3/8. Then for your second trapezoid, when x equals 1/2, y equals 3/4, and when x equals 1, y equals 3, this comes out to 15 over 4 divided by 2, that's 15 over 8. Then for our third term, when x equals 1, y equals 3, and when x equals 1 and 1/2, y equals 27 over 4, this works out to 39 over 4, but then you have to divide that by 2 because of this right here, and that comes out to 39 over 8. And then the same thing with our last term, we just have to do the same thing we've been doing before. So when x equals 1.5, y equals 27 over 4, and when x equals 2, y equals 12. So we get 75 over 4 when we give them a common denominator. Divide that by 2, we get 75 over 8. So when we add all of these together and multiply by 1/2, we get 8.25. And since we're asked to round to 4 decimals, we just add an extra 0, 0 to make sure that we fulfill the 4 decimal place request. So for this FRQ, we have a gravel processing plant. So we have an equation that tells us the rate at which unprocessed gravel arrives at the plant. We're told how much unprocessed gravel there is at the start of the day, how quickly the plant processes gravel, and we're asked to find out a few things about these different relationships. So for the first question, we have to find g prime of 5, and we have to interpret our answer. So the g equation, or the g function, is 90 plus 45 cosine of t squared over 18. The derivative of this is negative 5t sine of t squared over 18. So this is our derivative because the derivative of 90 is 0, so we can just leave that out. Then we have to do the derivative of the outside times the derivative of the inside. So we can take this t squared over 18. The t will drop down to the front, so we get 2t over 18, which is t over 9. That t over 9 times 45 is 5. The derivative of cosine is sine plus times the negative 1. So that negative 1 will just move to the front with our 5t, and then the inside stays the same, so we get negative 5t times sine of t squared over 18. Then when we plug in 5 using our calculator, we get negative 24.588. So the units for this number are tons per hour squared, and what this allows us to see is that the rate at which unprocessed gravel arrives is decreasing. Then for part 2 of the FRQ, we have to find out the total unprocessed gravel that arrives during the workday, so we can just do the integral from 0 to 8, since those are the hours of operation, of the rate at which unprocessed gravel is arriving, which comes out to be 825.551. So 825.551 tons of gravel have arrived during the hours of operation.
Okay.
In part C of the FRQ, we're asked to determine whether the amount of unprocessed gravel is increasing or decreasing at t equals 5. So we can evaluate this by taking our g function that we had earlier, which was 90 plus 45 times the cosine of t squared over 18. Since we're evaluating at t equals 5, we can plug in 5 to the t squared position, which is how we get the 25 over 18. We also have to subtract 100 from this total amount, since 100 is taken away after every hour, or 100 tons are taken away from the unprocessed gravel pile after every hour. And since we get a negative number from this equation, we know that the amount of unprocessed gravel is decreasing at t equals 5, since when the first derivative is negative, that means that the original function is decreasing. And then for part D, we had to find what the maximum amount of gravel during the day was, and we had to justify our answer. So we started by taking the same equation that we used up here and setting it equal to 0. We find that t is equal to 4.917. So then what we do is we evaluate the integral of this equation from 0 to 4.917, but we also have an original 500 tons of unprocessed gravel from the beginning of the problem that we have to add in as well. So we have the 500 plus this whole integral. So this whole integral came out to be 135.376 tons, and then the 500 original tons of unprocessed gravel get added to that to get this number. So as for justifying our answer and why the max occurs at t equals 4.917, prior to t equals 4.917, the amount of unprocessed gravel was increasing. After t equals 4.917, the amount of unprocessed gravel was decreasing. Then, because we know that this is our max, we can evaluate the integral from 0 to 4.917 to find the amount of gravel added during this time period, and then we just add the initial 500 to get 635.376 tons. And what I meant from the gravel added during this period is obviously there were more than 135.376 tons added during the 5-hour period at which unprocessed gravel was arriving, but we also have to factor in the fact that over time, since nearly 5 hours had passed, there were nearly 500 tons of gravel that were removed from the unprocessed gravel anyway, which is why this number is smaller than we may have anticipated.